So the topic of this presentation is normal critical values. This corresponds to Module 11, Topic 5 in the workbook. So what's a critical value of a normal distribution? So this point right here is the edge of the bottom 90%. So that X value is called the 90th percentile of the distribution. It's also called the 0.10 or 10% critical value of X. It's the X value that's at the edge of the top 10%. And so what we'll learn in this PowerPoint is how to find a point like that, where I give you a percentage to the left of the point, and then from that percentage you figure out, okay, so what's the X value that's located there? So this is kind of the reverse of the problem that we did in a previous section when we talked about probabilities under the normal distribution. There, I would have given you the X value and asked you to find the area, to find the probability to the left of that point. And in Excel, you would have used the norm.dist function to do that. This is the opposite problem. I don't give you the X value. I give you the probability, and you go backwards to find the X value. So the methods available to us to solve this problem of finding a critical value are really the same methods that we had for finding the areas. We had the graphical applets, the printed distribution tables, the calculators in Excel. So I've already, in the previous lecture, I demonstrated those graphical applets. I think you can just go back to each one of those websites and see how that works. I'll show you how to use the tables and Excel in the slides to follow. And I'll leave the calculators up to you. There's so many different brands. In the workbook, I do have instructions for the TI-84 calculator. Just as a reminder, here are the websites that we used for finding the probabilities, and these same websites also work for this reverse problem. So we want to use a printed table to find the z-score at the edge of the bottom 59.9% of a normally distributed population. So the edge of the bottom 59.9%. So I'm thinking about this blue area in the picture here being the 59.9%. And what I'm trying to find is the z-score, the position along the x-axis. I want to find the z-score right at the edge of the blue shaded 59.9% region. So how do I find that z-score in the table? So first, the areas, the blue shaded areas in the picture correspond to the numbers in the middle of the table, and I just go looking for the 59.9, and here on the third row I find 59.87. That's not exactly right, but it's as close as I can get in the table. That's the problem with the printed tables. They never have exactly any particular number that you're looking for, but you can get approximations. So this is pretty close. So I'm going to use this entry 59.87. That's the area. And then to find the z-score that goes with it, I'm going to find that the z-score is 0.25 STDs. Where did I get that? The 0.2 comes from the left edge of the table at the end of the purple arrow. Then where did I get the 5? That comes from the top edge of the table. So 0.25 STDs gives me the left tail area of 59.9%. So the critical z-score is 0.25. The subscript on the z-score, this 0.411, the way that notation works is, well, it's the critical z-score at the edge of the top 41.1%. See, the edge of the top 41.1 is the same as the edge of the bottom 59.9, and that's the point we're looking for. So it's a little awkward that the 60th percentile would be the 40% critical value. It's two different ways of speaking about the same z-score, 0.025 STDs either way. Okay, now if you know the mean and standard deviation of the distribution of x, and x has this normal distribution shape, then you could convert from STDs into natural units. And here's the formula for converting. The x is the mu plus z times sigma. You got to do the order of operations, right? You multiply z times sigma and add the mu. That gets you the x. And we'll practice that in the next slide. So here's an example to check whether you got it. Suppose human temperatures are normally distributed with a mean of 98.6 degrees Fahrenheit, standard deviation of 0.7 degrees Fahrenheit. Then 59.9% of the population would be cooler than what temperature? We know that temperature is 0.25 STDs, but what's that in Fahrenheit? Let's see if you can do the conversion. Now here's how you would do the same problem using Excel. You want to find the edge of the bottom 59.9% of the population for a standard normal distribution with a mean of 0 and a standard deviation of 1. This norm.inv function gives you that the edge of the bottom 59.9% is at 0.25 STDs. But you could also do the problem instead of for the standard normal distribution, you could do it with a mean of 98.6 degrees and a standard deviation of 0.7 degrees. So this norm.inv function, the inverse normal function, is okay with whatever units you want to use, as long as if you give it a mean and a standard deviation that are both degrees Fahrenheit, then the answer that comes out should be interpreted as degrees Fahrenheit. If you give the mean and the standard deviation in STDs, then the answer that comes out should be interpreted as STDs. You could do the whole thing in Celsius and it would all still work. So we got the same answer that we got in the previous slide where we were working from the table. Why is it called the inverse normal function? So in a previous presentation we had the norm.dist function. You use norm.dist when you have the x value and you want to find the area to the left. When you're going backwards, as you are here, when you're given the area and you want to find the x, that's the inverse problem, and you use norm.inv.